In older electrical systems, it's possible the neutral conductor might have been black instead of white. If the system underwent updates later, the original black neutral could have been mistaken for an additional hot conductor. Another possibility is a factory wiring error where the factory inadvertently included an extra hot conductor in the harness. It is also possible that the original installer may have employed non-standard wiring practices, such as using a different color code for the hot conductors. The extra hot conductor may have been installed as a backup in case one of the other hot conductors failed. Now let's discuss the purpose of the blue conductor. The blue conductor might be part of a control circuit that activates the ice cube relay. Ice cube relays are often utilized in heating, ventilation, and air conditioning, or HVAC systems to manage motors and solenoids. In certain motor applications, a capacitor may be connected between one of the hot conductors and the blue conductor to enhance motor performance. Regarding safety concerns, the presence of an extra hot conductor can result in misidentification and potential shock hazards if it is not correctly labeled. If the extra hot conductor is not properly sized, it could present an overcurrent risk if it becomes energized. Some recommendations include carefully tracing the circuit to ascertain the origin of the extra hot conductor and the function of the blue conductor. Clearly label all conductors in the termination box to prevent confusion in the future. Ensure that all wiring adheres to current electrical codes to minimize safety hazards. If you're not comfortable working with electrical systems, seek advice from a qualified electrician for assistance. Let's delve deeper into the potential causes and implications of finding an extra hot conductor in a motor hookup. It is crucial to understand the historical context of electrical wiring. Before standardized color coding became widespread, wiring practices varied significantly. Therefore, what appears as an anomaly today might have been acceptable or even common practice in the past. In older installations, it was not uncommon to find different colored wires used for neutral conductors, or even hot conductors, deviating from the modern standards of white or gray for neutral and black, red, or blue for hot. This lack of uniformity can create confusion and increase the risk of electrical shock, especially when working on systems that have been modified or extended over time. A neutral shift, as mentioned earlier, is a prime example of how historical practices can lead to misinterpretations. If a black wire was initially used as a neutral and later mistaken for a hot wire, it could create a scenario where the circuit appears to have an extra hot conductor. This situation is particularly hazardous because it can lead to unintentional energizing of components or equipment that are supposed to be grounded. The possibility of a factory wiring error should not be overlooked. Manufacturing defects, while rare, can occur, leading to incorrect wiring within the motor or its associated components. In such cases, an extra hot conductor might be present due to a mistake in the assembly process. This underscores the importance of thoroughly inspecting all wiring and connections before energizing any equipment, especially in older installations where documentation may be lacking. Non-standard wiring practices employed by the original installer can also contribute to the presence of an extra hot conductor. Electricians or technicians might have used unconventional methods or color codes, either due to a lack of knowledge or the availability of specific materials. While such practices might have been considered acceptable at the time, they can create significant problems for anyone working on the system later. A redundant connection, where an extra hot conductor is installed as a backup, is another plausible explanation. In critical applications, installers might have included a redundant wire to ensure continuous operation in case one of the primary conductors failed. While this approach can enhance reliability, it can also complicate troubleshooting and increase the risk of misidentification if the purpose of the extra wire is not clearly documented. Now let's shift our focus to the blue conductor and its potential roles within the system. Control circuits often utilize relays, such as the ice cube relay mentioned, to control various functions within the HVAC system. The blue conductor could be part of a control circuit that activates the relay, allowing it to switch power to the motor or other components. Relays are essential for controlling high current loads with low current signals, providing a safe and efficient way to manage complex electrical systems. A capacitor connection is another possibility for the blue conductor's purpose. In some motor applications, capacitors are used to improve starting torque, power factor, or overall motor performance. The capacitor may be connected between one of the hot conductors and the blue conductor, forming part of a circuit that enhances the motor's efficiency and reduces energy consumption. It is important to know that capacitors can store electrical energy even after the power is disconnected, so caution should be exercised when working with them. Addressing safety concerns is paramount when dealing with any electrical system. The presence of an extra hot conductor, regardless of its origin or intended purpose, can create significant hazards if not properly identified and labeled. This identification can lead to accidental contact with live wires, resulting in electrical shock or electrocution. Therefore, it is crucial to take all necessary precautions, such as wearing appropriate personal protective equipment, using insulated tools, and verifying the absence of voltage before working on any electrical components. Overcurrent protection is another critical safety consideration. If the extra hot conductor is not sized appropriately for the current it may carry, it could pose an overcurrent risk. This means that the conductor could overheat and potentially cause a fire if it becomes energized. To prevent this, it is essential to ensure that all conductors are properly sized and protected by circuit breakers or fuses that are rated for the appropriate current. Following the recommendations outlined earlier is essential for ensuring electrical safety and preventing potential hazards. Tracing the circuit carefully is the first step in understanding the purpose of the extra hot conductor and the blue conductor. This involves visually inspecting the wiring, following the conductors from their source to their termination points, and using a multimeter to verify their continuity and voltage. Labeling all conductors clearly is crucial for preventing future confusion and ensuring that anyone working on the system can easily identify their purpose. This should include marking the voltage, function, and any other relevant information on each conductor. Adhering to current electrical codes is essential for minimizing safety hazards and ensuring that the installation meets the required standards. Electrical codes are constantly evolving to reflect new technologies and best practices, so it is important to stay up to date on the latest requirements. If you are not comfortable working with electrical systems or if you encounter any unfamiliar situations, it is always best to consult a qualified electrician. Electricians have the training, experience, and tools necessary to safely and effectively troubleshoot and repair electrical problems. In addition to the specific recommendations mentioned above, there are several other steps that can be taken to enhance electrical safety and prevent potential hazards. Before working on any electrical system, it is essential to de-energize the circuit by turning off the appropriate circuit breaker or fuse. This will help to prevent accidental contact with live wires and reduce the risk of electrical shock. Use a voltage tester to verify that the circuit is de-energized before proceeding with any work. This will provide an additional layer of safety and ensure that the circuit is not still energized. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses, to protect yourself from electrical shock and other hazards. Insulated tools should be used to prevent accidental contact with live wires. Inspect all wiring and connections for signs of damage or deterioration. Replace any damaged or worn wires or connectors to prevent potential problems. Ensure that all electrical boxes and enclosures are properly grounded. Grounding provides a path for fault current to flow back to the source, helping to prevent electrical shock and reduce the risk of fire. Test ground connections regularly to ensure that they are functioning properly. Install ground fault circuit interrupters, or GFCIs, in areas where there is a risk of water exposure, such as bathrooms, kitchens, and outdoor locations. GFCIs are designed to detect ground faults and quickly shut off the power, preventing electrical shock. Follow all applicable electrical codes and regulations. Electrical codes are designed to ensure the safety of electrical installations and prevent potential hazards. If you have any questions or concerns about electrical safety, consult a qualified electrician. Electricians have the training and experience necessary to safely and effectively address electrical issues. By following these recommendations and taking appropriate precautions, you can help to ensure electrical safety and prevent potential hazards. Remember, electricity can be dangerous, so it is always best to err on the side of caution.